Hello, I'm Luis Serrano, and this video is about autoencoders. We're going to talk about denoising and variational autoencoders. Autoencoders are a very popular generative model. If you enjoy generative models, this video is part of a series which also includes generative adversarial networks and restricted Boltzmann machines. Check them out. The links are in the comments. The way I imagine autoencoders is like this. Imagine that you want to understand a book. So what you do is you call on your very smart friend Aisha. Aisha's job is to summarize the book into a few pages for you to understand it. Now, how do we measure how good a job she did? What we do for this is we call our other very smart friend Berta, and we give Berta the job of rewriting the book completely using Aisha's summary. And then we measure how both of them did by comparing the original book with the one that was written. Obviously, it's very hard for them to be able to reproduce a book completely word by word, but imagine that they get really good at this task. What would their strategy be? Well, it seems that for them to be able to do this job really well, Aisha would have to really nail down the main ideas of the book as concretely as possible, and Berta would have to get very good at writing a book based on these ideas. The main idea here is that by forcing Aisha and Berta to crunch down the book into a few pages, we force them to really understand it well. That is what autoencoders do. We force them to dramatically simplify the data and then to build it back up, thus forcing them to extract as many useful features of it as possible. Now, in rough terms, imagine that we call the dimension of the book the number of words on it. Thus, we reduce the dimensionality of the book by summarizing it into a few words, and then we increased it again. This is what we call this a dimensionality reduction algorithm, and it is part of unsupervised machine learning. Now let's get into a more real-life data set, say images of faces. The data set is encoded by many numbers as we need different numbers for the color of each pixel. The job of Aisha, who's now called the encoder, is to summarize this dataset into one with less numbers, say describing the size of the eyes, the color of the hair, and other features of the images. Then we take these features to Berta, called the decoder, who will help us reconstruct the faces from these numbers. The dimension of a data point is the amount of numbers used to encode it. In this case, we went from many dimensions down to a few, and then back to many dimensions. As I've hinted before, an autoencoder comprises two parts, an encoder that shrinks the data and a decoder that blows it back up. The idea is that what comes out should be very similar to what comes in. The shrunk or simplified data is called the latent space, which in principle summarizes our data and compactifies it in order to get good insights from it. A very useful type of autoencoders is denoising autoencoders, which are trained to take on corrupted data such as noisy images and returns a clearer, crisper version of that image. Another very important type is variational autoencoders, which are trained to generate new data. For example, if we train it with handwritten digits, it generates more new handwritten digits that it hasn't seen before. The way the variational autoencoder generates new data is by picking them from a latent space, which is a simplified version of the space of data. And by simplified, I mean lower dimensional, which I will explain later. Variational autoencoders are very good at generating high-resolution images, such as faces, and these over here are some samples of faces generated by a variational autoencoder. The main concept to understand before we get into autoencoders is the concept of dimensionality reduction, and for this we'll use an example. The sample dataset that we'll use in this video is a dataset of images. These are pretty simple 2 pixel by 2 pixel images where each of the 4 pixels has a different color. They are red, blue, yellow, and green. And each pixel has some intensity, which is any real number between 0 and 1. The intensity is highest at 1, where the pixel is full of its corresponding color, and the lowest at 0, where the pixel is white. Each data point is described by 4 numbers, namely the 4 intensities. For example, in this image, red has an intensity of 0.5, blue of 0.7, yellow of 0.35, and green of 0.65. Since each data point is described by 4 numbers, the dataset is 4-dimensional. Each dimension corresponds to one of the colors. But now we start looking at the images more carefully and we notice something peculiar. Can you notice it? The peculiar property of these images is that the intensity of the pixels in the upper right and lower left corners are the same. Similarly, the intensity of the pixels in the upper left and lower right corners are also the same. That means the intensity of red is always the intensity of green, and the intensity of blue is always the intensity of yellow. So all of a sudden, the dataset is no longer 4-dimensional, as we don't need 4 numbers to describe each data point. Now we only need two numbers to describe it. The first one is the intensity of red, which is the same intensity of green. And the second one is the intensity of blue, which is the same intensity as yellow. So in this case, the image is described by two numbers, 0.8, which is the intensity of red-green, and 0.65, which is the intensity of blue-yellow. Therefore, this data set is now two-dimensional. Since the data set is two-dimensional, we can actually plot it in the plane like this. For every pair of values x and y between 0 and 1, there's an image with x intensity of red and green and y intensity of blue and yellow. This will appear later, but this is called a latent space. However, assume that we haven't noticed this diagonal property and we still think the dataset is four-dimensional. This is where the autoencoder can help us. The goal of the autoencoder is to identify these dependencies in the original dataset and use them to shrink the number of dimensions. In other words, to summarize the dataset using less numbers. In this case, the original images are described by four numbers, but the autoencoder figures out that only two are needed. So it encodes the dataset using these two numbers. The decoder then uses these two numbers to reconstruct the data again, namely to rebuild the images in the original dataset. The most important part of the autoencoder is that it understands the data by forcing it to pass through a small gap. In the same way that our friends Aisha and Berta managed to understand the book well by summarizing it into a few pages and then rewriting it, the encoder and decoder understand the data by summarizing it and then rewriting it. In general, some information is lost during this process, but the autoencoder is trained so that as little information as possible is lost. So how do these encoders and decoders work? In real life, they are neural networks, but we'll get to that later. For now, let me show you a very simple encoder and decoder that work with this dataset. Imagine that we have this image where the pixels in one diagonal have intensities of 0.8 and the ones in the other diagonal have intensities of 0.6. The encoder would have to extract these two numbers, 0.8 and 0.6, thus obtaining a summary of our data, which as we've seen is called a latent representation. The encoder then passes this information to the decoder, and the decoder's job would be to reconstruct the image based on these two numbers, 0.8 and 0.6. Now I invite you to give it a try and try to label the edges in such a way that this works. And I'll show you how I did it. So it's done with a very simple architecture. The edges denote multiplication by the number in the edge. So let me show you. Here's our image again with the intensities of the four pixels 0.8, 0.6, 0.6, and 0.8. In order to calculate the output of the encoder, we'll multiply 0.8 times 0.5 and add it to 0.8 times 0.5 because this is what the edges indicate. So we get 0.8. In other words, we get the average of the intensities of the red and green pixels. We do the same thing with the other two pixels. So for the second value, we get 0.6 times 0.5 plus 0.6 times 0.5, which is 0.6. And there is our summary, or our latent representation, is the numbers 0.8 and 0.6. They are the values of the intensities at each diagonal. And now, in order to decode it, we simply put ones on the edges of the decoder. So the values are going to be 0.8 times 1, 0.6 times 1, 0.6 times 1, and 0.8 times 1. So we have successfully reconstructed the image. But now let's see what happens if we throw in an image that is not in our dataset. Say this one was intensities 1, 0.6, 0.2, and 0.4. This image is not on the dataset because the intensities are not the same on the two diagonals. Recall that for an image to be in the dataset, the intensity of the two diagonals have to be exactly the same. When we pass the image through the encoder, the latent representation or the summary is the two numbers 0.7 and 0.4, because for the number on top we get 1 times 0.5 plus 0.4 times 0.5, which is 0.7, and for the second number we get 0.6 times 0.5 plus 0.2 times 0.5, which is 0.4. We then pass this information to the decoder, and the decoder decodes it as 0.7 times 1, 0.4 times 1, 0.4 times 1, and 0.7 times 1. So it gets the image with intensities 0.7, 0.4, 0.4, and 0.7. This is actually called a denoising autoencoder, and I'll show you why. This is what we did. We started with this image that is not from our dataset because it doesn't satisfy the diagonal condition. And now the autoencoder reconstructed it as this one. So it cleaned it up. It turned it into an image that now is part of our data set. So that's one great property of autoencoders, and it's at the correct noise when the images are noisy. In image datasets, we can use a denoising autoencoder to remove noise like this, to reconstruct a part of the image that is missing, or even to add features to images such as glasses or hats in a human face, etc. The autoencoder that I just showed you is actually a linear autoencoder, so it can be found with methods using linear algebra such as matrix factorization or singular value decomposition. If you'd like to learn those in detail and figure out how we built the previous autoencoder, check out these videos in my channel. However, as I mentioned before, most autoencoders are neural networks which are more complicated than this. So this is what I'm going to show you next. As I mentioned, to understand autoencoders, one must have an idea of neural networks. The remaining of this video is still self-contained as we'll introduce everything needed, but if you'd like to get the most of it, I recommend you to look at some other videos I have on perceptrons and neural networks. Here they are, and the links are on the comments. For the rest of this video, there are several calculations which you can follow along in the GitHub repo for this video at github.com, Serrano, autoencoders. The link is in the comments. So in order to harness the power of the neural network, let's change the dataset a little bit. Let's say now that our images still have the diagonal property, namely that the red and green pixels have the same intensity and the blue and yellow have the same intensity as well. But now the pixels either have an intensity close to 1 or close to 0. Almost no image has pixels with intensities in the middle. That means our images are either fully white, fully colorful, or only one of the two diagonals is colored and the other one is white. For this dataset, we need an autoencoder with a neural network structure, and by that, allow me to introduce a very important function. The function is called a sigmoid, and it is useful when we want to turn scores into probabilities. A score is any real number, positive or negative, and a probability is between 0 and 1. So what we do is the following projection, where the sigmoid of 0 and 1 are technically minus infinity and plus infinity, the sigmoid of 0 is 0.5, and any real number gets mapped into something between 0 and 1. The graph of the sigmoid function is this one, and the formula is 1 divided by 1 plus e to the negative x. Here's the graph. As an example, sigmoid of 1 is 0.73. And here are some other values. And for building the autoencoder, we also need the notion of a perceptron, the building block of neural networks. A perceptron has inputs such as 1, 2, 3, 4 here, and edges with weights such as 1, 0.5, minus 3, and 2. The perceptron also has a bias, such as minus 2 here. What the perceptron does is that it multiplies the inputs by the weights and adds them, then adds the bias, and gets a value. In this case, we get a value of 1. That's also called the score. Then it applies the sigmoid function to get 0.73. This is similar to what we saw in the first autoencoder, except for the sigmoid function. And so if we remember the first autoencoder we saw, it contained several perceptrons, except without the sigmoid function. So our new autoencoder is exactly like the ones before, except this one does contain the sigmoid function to pass the output of the encoder into the input of the decoder, and another sigmoid function to process the output of the decoder. On the encoder, the weights are all 10, and the biases are minus 10. And in the decoder, the weights are again 10, and the biases are minus 5. So for example, let's start with these images with intensities 0.8, 0.4, 0.4, and 0.8, and let's see what the autoencoder does to it. 0.8 times 10 plus 0.8 times 10 minus 10 is equal to 6. 0.4 times 10 plus 0.4 times 10 minus 10 is equal to minus 2. So the output of the encoder is 6 and minus 2. Then we apply the sigmoid function to both to get 1 and 0.1. These numbers are rounded. These two numbers are the latent representation of our image. Finally, we pass them through the decoder. Notice that 1 times 10 minus 5 is 5, so the first and last scores are 5, and 0.1 times 10 minus 5 is minus 4, so these are the two middle scores. Finally, we apply the sigmoid function to get the intensities 0.99, 0.02, 0.02, and 0.99, which gives us this image over here. Notice how the autoencoder turned the image into one where the colors are close to 0 or close to 1 as intended. So as I mentioned before, these are called denoising autoencoders because they turn images that are not likely to be in the dataset into images that are likely to be in the dataset. Let's look at some examples. And recall that the dataset is formed by these four types of images. Either you have one diagonal, all white, or all colored. The examples that follow are all calculated in the repo. So if you'd like to follow along, feel free to take a look and maybe even try some new images and see what the autoencoder does to them. So here's a noisy image. This one has colors, but the intensities are not close to 0 and close to 1. So it's not in the data set. And what the autoencoder does is says, well, your 0.6 diagonal, I'm going to strengthen it, and your 0.4 diagonal, I'm going to weaken it, so that we get something that is in the data set because the red-green diagonal is strong and the other diagonal is not. Similarly with this one, where the blue-yellow diagonal is a little stronger than the other one, so it fully strengthens the blue-yellow diagonal and weakens the red-green one. Here are some other examples. Take a look at this one. This one seems to be the red-green diagonal, right? The upper left, lower right diagonal, except that the upper right pixel, the blue one, is miscolored. It has an intensity of 0.5, but maybe it should have 0. So the denoising autoencoder says that. It pretty much says the closest image that I can find in the dataset to this one is one where that blue pixel is not colored at all. Same thing over here. This one seems to have a blue-yellow diagonal colored, except that the bottom left pixel seems to be lighter than what it should. It's a mistake. So the denoising autoencoder says, okay, look, I fixed it for you. I strengthened the yellow color so that now we have something that pretty much is in our data set. Let's look at some more examples. This one over here seems to be a fully colored image except for that bottom right green pixel there, which has a 0.2. Well, the denoising autoencoder colors the entire picture for you. And finally, one over here, which seems to be a white picture except for that 0.8 upper right blue pixel. Well, the denoising autoencoder figures out that it should be a white picture, a white image, and turns that blue into white. So again, I encourage you to check out the repo and try with some images and see what happens. But in summary, what these autoencoders did is they take any image and they say, I'm going to try to force it to be one of the images in the data set that you trained me for. Now, the autoencoders we've used only have one layer. As you may imagine, this is not always the case. In order to harness all the power of neural networks, autoencoders can have many layers and also complex architectures such as convolutional or recurrent layers. Here's an example of a convolutional autoencoder that is used to denoise images of handwritten characters in MNIST. As you can see, this type of denoising autoencoders do a very good job cleaning up noisy images. Now let's get to another very interesting property of autoencoders, and it is that they can generate new data points, for example, new images. And we're talking about completely new images, not copying the images that appear in the dataset, but images that are completely new, completely out of the blue, that are made to look a lot like the images in the dataset. And in real life, this is amazing because the autoencoder can generate pretty good images, can draw the face of a person that doesn't exist or a handwritten digit that has never been drawn before. And the way we generate these images is by forgetting about the encoder and only focusing on the decoder. Recall that the encoder used to output some numbers, 2 in this case, which were the latent representation of the image. Well, now that we don't have the encoder, we can simply pick any 2 numbers, say x and y, and that's our latent representation. And now we can use the decoder and it will generate an image for us. This gives us a nice visualization of the latent space. Check this out. Let's say that we give the decoder the numbers 0.3 and 0.8, and it'll generate the following image with intensities 0.12 and 0.95. And so what we're going to do is we're going to plot the latent space over here, where the first coordinate, the 0.3, is going in the horizontal axis, which corresponds to the red-green diagonal, and the second coordinate, the 0.8, goes in the vertical axis, which corresponds to the blue-yellow diagonal. And so this image will be located over here. That corresponds to the image. And as you may imagine, the latent representation normally has more than two numbers or more dimensions, so we wouldn't have a plane, but we would have a higher dimensional space. But this is still okay, because what we did is we managed to crunch a space of images, which is very high dimensional, into a space of less dimensions, thus simplifying it. Now we can see the latent space as this entire square, where each point corresponds to an image, and as I said before, the axes correspond to the two diagonals of the image. So if we associate each point to the image and each axis corresponds to the intensity of the diagonal, then as we move to the right, the intensity of the red-green diagonal increases, and as we move from bottom to top, the intensity of the blue-yellow diagonal increases. And a nice way to visualize the latent space is like this. Now, notice that we can pick any point from this latent space uniformly, which is the same as grabbing those two numbers and putting them through the decoder. So we can generate every one of these images with the same probability and the same likelihood. But what if that wasn't the case? What if the dataset only contains some of these images, but not the other ones, and we wanted to generate only those? It happens very often that the latent space is too big and it's full of noise, and the good images only live in a small portion of it, so we want to grab that portion. So for example, what if the images in our dataset we were all in a small oval over here? Can we train the autoencoder to only generate those, or at least to generate them with a much higher probability than the rest? We can, and that's where variational autoencoders come into play. So let's say that the center of the area we want to generate the images is this point over here, with horizontal coordinate equals to 0.6 and vertical coordinate equals to 0.8. And we actually also care about the spread, or how wide is this region in each of the coordinates. And the spread is very much related to the variance if picking this point was a random variable. So the more variance, the more the point is all over the place, and the less variance, the more that the point is fixed closer to the average. If you'd like to know more about variance, I have a video in the comments that you can take a look. So what we're going to do now is we're going to train two normal distributions, one that will generate the horizontal coordinate and the one that will generate the vertical coordinate, in order to pick points that are very likely to be inside this oval, and in particular likely to be towards the center. And again, if you don't know what a normal distribution is, no worries. Just think of selecting random points under the pink and green curves so that the points underneath the fat area of the curve are more likely to pick than those points at the tails. So when we start selecting points out of these two distributions, we start seeing that, as we expected, most of them are inside this oval, and the occasional point is outside. So these pairs of coordinates are going to be useful to generate our images, because that's going to be the latent representation, and that's what's going to get passed to the decoder. So in more detail, this is what happens. We generate points in the latent space by sampling out of the first distribution, which let's say has a mean of 0.6 and a variance of 0.2, and from the second distribution that has, let's say, a mean of 0.8 and a variance of 0.5. And let's say the point generated by the first distribution is 0.7, and by the second one is 0.83. Now we pass those 2 points by the autoencoder, and we're going to get the image with colors 0.88, 0.96, 0.96, and 0.88. Now you may be wondering, how do these autoencoders get trained? And the training is not very different than with any other neural network. It's using an error function or a loss function. Now I'm going to gloss over the details, but if you'd like to learn more about the loss function, check out this video on my channel, which is in the comments. Now let's start by training a regular autoencoder, and then I'll show you how to train a variational one. The loss function is crucial as it measures how well the neural network is doing. More specifically, this loss function is high when the neural network is not doing well, and small when the neural network is doing well. In this case, imagine that we have this image with numbers 0.8, 0.4, 0.4, and 0.8. And we initialize the autoencoder with random weights. We pass the image through the autoencoder and the decoder, and we get this image with numbers 0.16, 0.75, 0.69, and 0.35. That is a very bad image because it looks nothing like the original one. Recall that the goal of the autoencoder is to reconstruct the original image. The autoencoder, this one over here, has a large loss function at this data point because it didn't do very well reconstructing the image. In contrast, this autoencoder over here managed to output an image that is very similar to the input. As you can notice, these numbers are very similar to the input numbers. So this autoencoder did very well, and therefore it has a small loss function. And the training process consists of minimizing the loss function through a process called backpropagation. And once you minimize this loss function, you get an autoencoder that has a great set of weights that manage to reconstruct your data set. So we're going to start by initializing the autoencoder with random weights. Now for every image in the data set, we're going to look at the output and cook up something called a reconstruction loss, which measures how similar are the input and the output. So this is the loss we're going to minimize. And in general, this is how we train the autoencoder. We initialize the encoder and the decoder with random weights. We calculate the reconstruction loss in the data set or in a batch or per image, and then we do backpropagation to update the weights. So what is the reconstruction loss? Well, it can be several things. One of them is the mean square error, in which we simply take the difference between the values of each pixel and in the input and the output. If the input is the image at the left and the output is the image at the right, then the mean square error, or MSE here, would be 0.0046, which is quite low, which makes sense since the images are similar. And again, these calculations are all done in detail in the repo if you'd like to take a look. For the other case, where the input and the output are quite different, the loss function is 0.8625, which is much larger. So this is a good reconstruction loss because it measures how far are the input and the output. Another function that works is the log loss, and this is more for examples in which the images have pixels that are only 1 or 0. This is the formula for the loss function. It may look strange, but it's very common in neural networks, and it can be seen as a negative logarithm of the likelihood. And again, it gives a small loss for images that are close to each other, such as this one, where it's 0.421. And it gives a large loss for images that are far away from each other, such as these ones, where the loss is 6.438. So that reconstruction loss is the loss function that we use for training regular or denoising autoencoders. Now, how do we train a variational autoencoder? Well, it's very similar. All we have to do is modify the loss function. So recall that for regular autoencoders, we had a reconstruction loss that tells us how different is the input from the output. For a variational autoencoder, we simply need to add a term to this loss called the latent loss, and it works as follows. First, recall that attached to each node in the latent space, there is a normal distribution. These are called latent distributions. We now look at a batch of data, not just one point. So we have a set of data and a set of generated data. And the latent loss is going to come out of there. As a matter of fact, we only need to worry about the encoder. So we start with two random normal distributions, say the pink one with mean mu1 variance sigma 1 and the green one with mean mu2 and variance sigma 2. And as I mentioned before, we're going to take a batch of data and we're going to see where each point gets mapped in the two coordinates in the latent space. We're going to map each one of the points, and we're going to collect this information in order to train our distributions pretty well. So now that we're done mapping our points, this is what we do. We're going to calculate how far is the distribution of our mapped points from the original distribution we had. And this distance or this difference is called the latent loss. And I'll tell you in a minute how to calculate the latent loss, but the idea is that when the distribution that we have is close to the distribution of those points we map, the latent loss is low, and when it's far, then the latent loss is large. So using this latent loss, we're going to be able to train two good normal distributions at the same time as we train our model. So as I promised, let me show you the latent loss. So the latent loss can be many things, as long as it's a function that gives two similar distributions a low loss and two very different distributions a big loss. So this is because the goal of the latent loss is to be an alarm that tells us when two distributions are far apart as we want them to be close. So one example of a good latent loss is the KL divergence, which is given by this formula over here. The formula comes from entropy and maximum likelihood. So if you'd like to understand a bit more, check out this video also in the comments called Shannon Entropy and Information Gain, where you can take a deeper dive into these type of equations. But now let's look at an example of KL divergence. So let's say we have these two distributions, P and Q, which are very similar. So we're going to use the formula to calculate the KL divergence, and we get 0.132, which is a low number. Now let's take these two distributions that are quite different, and we calculate the KL divergence to be 0.583. So as you can see, it's larger. And again, these calculations also appear in the GitHub repo, so you can take a look, as well as the functions are coded and all that. So in summary, the way to train a variational autoencoder is similar to the way to train a regular one. First, we initialize the encoder, decoder, and latent distributions with random weights. And then we calculate the reconstruction loss plus the latent loss, and finally do backpropagation to update the weights. Variational autoencoders can generate really good images. Here's an example of a latent space of images of human faces. And as I mentioned before, if you enjoyed generative models, this video is part of a series which also includes generative adversarial networks and restricted Boltzmann machines, so feel free to check them out. The links are in the comments. So that's all, folks. Thank you very much. If you like these explanations, I encourage you to take a look at my book, Grokking Machine Learning, in which I talk about machine learning in very simple terms using pictures, examples, lots of codes, and real data sets. Here's a 40% discount code for you to use if you'd like to buy it. You can check the link in the comments of this video. And if you like this video, I invite you to subscribe to the channel for more content. Also, please hit like and share it and comment on it. I love reading the comments. In particular, if you have topics you'd like to see, feel free to suggest them over here. You can also tweet at me. My Twitter handle is LuisLikesMath. And you can also view all these videos and other information in my page, Serrano.academy. And so that's all for now. Thank you very much for your attention, and see you in the next video.